Okay, good morning. Welcome back from the long weekend. All right, so it looks like we have a fuller house today than last Friday. So last Friday we started chapter 13 module, and while I didn't take formal top hat polls to gauge people's levels of comfort, familiarity, or memory of Gen Chem and some concepts you may have seen in general physics or intro to physics, it was clear to me based on some of the responses that either you don't remember a lot of things, or that you are, but you're kind of shy and didn't speak up. So I thought today we would just recap a little bit of what was talked about on Friday, just so everybody's comfort level is, more of the same than on Friday. And we'll have some top hat questions to refresh your memory as well and engage you a little bit more. I also updated the slides, not so much in the first half of the deck. It's more so towards the latter half, mainly due to the response that I saw on Friday. So that way it will give us more problems to talk about, to discuss some of the concepts. Also, I wanted to clarify page 1, which says you should read chapter 13 except for the 13.4 section. So that goes over ferroelectric materials, such as like barium titanate, lead titanate, those sort of compounds. We won't be discussing those concepts, at least in this semester. So you're not responsible for that section, and your homework would also reflect that. And homework, of course, is also due next Sunday. It should be open by this afternoon, 2 p.m. So anyway, look out for that. Okay. Any other questions before I start? Okay. And today I did bring the good old papyrus-based technology in case all of this goes, which, as we know from Friday, there's a gremlin in this room, and it will not get the better of us. So I have come prepared. All right, so electronic properties, so excited. We've been building up to this. We've been building up to every single module, so it's not that unique. But we've been building up on discussions of materials properties, right? Atomic bonding, all of that. And we discussed a little bit of that on Friday. So we're going to crunch some numbers today to get that point across. But we've been building up, how do we understand an atom? How do we understand the components of an atom and how it interacts and bonds with another atom, right? We had lengthy discussions of that, and now it all comes to a head. It comes down to how do you manipulate electronic properties. So basically all of your iPhones and Samsung phones and whatever phones you may have can run as well as it does, right? And it really comes down to basically engineering the number of charge carriers as well as the mobility of your material. That's it. I mean, the only reason why anything on this podium runs and anything in your back pocket runs is because of that, is because Intel has gotten really good at engineering where every single electron goes and where every single hole goes. And they continue to do this really well. And of course, we're now pushing our limits. If we get to it by the end of today, we'll talk about the limits of microstructuring, nanostructuring material. We talked about microstructure, right? We talked about how that affects mechanical properties, how changing just the microstructure, so grains within the material, affects the overall strength, ductility, all that jazz from chapter 6, right? Now we're going to talk about what happens when you go even to a smaller limit. right? And this goes back to, I believe, one of the first few questions that I asked, and I think Kyle was the one who answered it and said, we need a scanning electron microscope or some sort of microscope beyond the optical microscope to image these things, right? And that's where we are now. We're at the limit where not only can we not see things, quote unquote, as well, image, really, we don't see things anymore, we image things, but now we can get channels down to where we can't even make the channels. They're beyond the limits of lithography. So what do we do now? So now you're entering the age of quantum computing and all of that, and you don't know it yet, but we're there. So, okay, so this is like 1940s, 1950s Bell Labs type of technology that you're learning. It has relevance today, but this theory has been developed for the last 60 years to the point where we think we understand how electrons and holes behave. So if you get this down, you now caught up with 1947 technology, okay? Okay, so let me skip to this. Ooh, hold on. Oh, dear. Oh, I made the mistake of exiting, which, as Professor Dupay said, never end, right? Because their pen will go away. But we're already there. So, oh, Jesus Christ. Okay, so we went through all of that. So let me see. This was where, oops, sorry. I want to pick up with band theory because the band gap absolutely affects the rest of our discussion. Okay, so it looks like the pen is still there. So we talked about the band gap, and everybody had this face of what are these curves. You've seen it before. It's energy versus interatomic distance. It's just colored differently and from a different textbook. That's all, okay? So we talked about when two atoms come together, right? Let's say you have hydrogen or you have sodium, whatever. It doesn't matter. You have some bands, you have some energy levels, right? You have your 1s2, 2s2. I keep saying these things because that's what we're dealing with. So you have all that. And we talked about, okay, what happens when you bring two atoms together? That was this, right? You start to form these bands. You start to form bonding orbitals and antibonding orbitals. Okay, so this is nice block-ish cartoon type diagrams, okay? So it simplifies our thinking, but in reality, this is what's happening. So the energy diagrams that you worked with in chapter 2, when you're talking about, is it energetically favorable for me to be at a bond distance A away from another atom? That has everything to do with this, right? These were the curves that you saw. Let me draw a little bit better, right? Do you remember something that looks like that? E versus bond length, where you have some equilibrium interatomic spacing. We used to call that A naught, remember? And you dealt a lot with the energy, the depth of the energy well, the bond vibration, all of that. Okay, so you work with that. This is now the bonding energy state. This is the anti-bonding, and in between what we talked about before, where there are all these states, right, that split due to quantum mechanics. There are all these states, but from far away, you don't know any better. If you're just another element coming in to the system, if you're another dopant or whatever, you come to the system, you see these bands, right? Because there's 10 to the 18, 10 to the 20 atoms, 10 to the Avogadro numbers atom. These are the bands that you see. But the splitting is fine. So within the splitting, you have all these energy bands. Okay. So these splittings correspond to this. Okay.
So they always define where exactly that splitting point is that lets you measure your gaps?
Your gap is the split here, this energetic state. So it's really here. Okay, hold on.
So you could put that like at any point along with the distance between the curves at no matter what point?
Particularly at the equilibrium point. Yes, you can discuss the band gap at any point, but nobody's interested in that in the sense of we don't deal with those conditions for real material. Real materials, we have an equilibrium interatomic. Correct, yeah. So your energy diagram, without these bands, determine where your interatomic bond distance is. So that's one. Irrespective of all of these bands. Just two atoms in the hypothetical sense, in vacuum, 0 Kelvin, 0 pressure, just coming in, right? You have this A naught. And then when you put a whole bunch of A naughts together, right, you get these bands. So you have your you have your valence band, you have your conduction band up here, and then these are your core states. So let's say you have lithium, right? 1s2, 2s2, 2s1. Okay, 1s2, 2s1. That's based on looking at your periodic table. So your lithium is half filled. So this is your core, your 1s2. So maybe that's not such a good example. Maybe we need to go to something like carbon, right? Carbon 1s2 is your core states. They don't really interact with anything. It's the valence electrons. I keep circling it because this is going to be very important. Okay, those are the electrons that you need to care about, because those are the electrons that either get excited when you input, let's say, light or temperature or whatever in your semiconductor material, right? So if you're dealing with silicon, the valence electrons are what you care about. Okay, so if you're an ECE, you probably have heard all of this. You know how to band engineer silicon and cadmium sulfide and gallium arsenide to death. So for everyone else, this is going to be not a review. Okay, so hopefully that clears things up in terms of what these curves look like. They're just your bond, your energy versus bond distance diagram. Okay, but now there's an anti-bonding state that's up here. So all you really have to concern yourself with is that there's a band. Okay, and there's some distribution, and now you have a gap. And if you're a semiconductor, if you want to have increased conductivity, you're going to have to input some sort of energy. Either it's some photons, i.e. light, or temperature, so that you can get your charge carriers to start conducting. Right? That's what you're concerned about. Okay. So that was that. So I believe we ended here last time talking about the different states and the different bands, different types of materials, and what the band structures look like. What you already intuitively know, right? Metals conduct because they don't have this gap. In semiconductors, and we'll talk about the difference between intrinsic semiconductors and extrinsic semiconductors, they have this band. So if you're an electron in this valence band here, and you want to be excited and get up to here into your conduction band, you need some sort of energetic input, okay? And we sort of talked about that a little bit. Oh, sorry, that's insulator. Sorry, I marked insulator. Same thing though. It's just the band gap for insulator is larger, right? So typically when we talk about insulators, we're talking about materials with like 5 eV. A band gap. That's a really large energy barrier to overcome, even with temperature. And so I think we'll crank out some numbers to demonstrate that in just a few slides. But this is where we left off for band diagrams. And then you see here this E sub F, this Fermi energy, right? We say that level, the Fermi energy or the Fermi level, is going to be where your bands, the highest energy for the band that's filled. So here you could see, okay, if you have some filling, let's say in lithium, right, 1s state, 1s1, it doesn't fill 1s2 completely, right, because you can put 2 electrons in there, but it's partially filled. So you're going to have some empty states, you have some filled states, so we define the Fermi energy to be where it's highest, to where it's filled in terms of the energy states. If you still have a metal and it gets filled up to here, now your Fermi energy has moved up. That's just by definition. If you have an insulator or semiconductor, right, you have electrons that get filled up in the valence band up to here, but we define actually the Fermi energy for these types of materials to be right in the middle of your band gap. So whatever your band gap is, divide that by 2, that's going to be your Fermi energy. And that's just a definition. We put it smack in the middle. This is for a semiconductor or an insulator that we haven't done anything to it. And by that, I mean we haven't added any dopants, we haven't added any impurities, we haven't done anything to it. It's just your pure material. So if you have silicon, and this is your band diagram for silicon, say, and you have a band gap let's say you have a band gap of 1.1 eV, right? So silicon would then, your Fermi energy would be at half of that. Divide that by 2.5 something, blah, blah, blah. Okay. Just the definition. Okay. So, review. Before we go on semiconductors, let's review your understanding of conductivity, or rather, inverse of that, resistance of a wire for metals, because semiconductors will be different. What was that comment? I didn't hear it. Check any or all. You should be able to. There's rumbling, is it not? You can only pick one. Oh, this is the worst, you know. Okay, well, based on that question and based on the rumblings, clearly there's more than one. So just mark something. And we'll discuss it as a group. We can discuss them one by one based on what you pick. Feel free to talk to your neighbor. If it's A, B, C, D, combinations thereof, or all of the above. All right, we're just about there. And since you're getting full credit for this anyway, due to Top Hat being Top Hat, let's start discussing. Okay, who says A? Okay, most of you. At least those that choose to raise their hands. Okay, B? Okay, so about same. C? Ooh, less so. Interesting. Okay, we're about out of time anyway, so get your answers in. Or D? Okay, so there seems to be visually a consensus for A, B, and D, but not C. Those of you who said C, temperature of the wire would affect your resistance of the wire, who would like to share why you think C is also correct? What was that?
That's how temperature sensors measure temperature by the resistance.
Yeah, so what's your name?
Jeff.
Jim?
Jeff.
Jeff. Okay, so Jeff said that you can measure temperature with wires, right? You measure the resistance. So you're describing a thermocouple, basically. Well, and depending on the temperature range that you want, you have different materials or different chemistries, right? So absolutely, temperature of the wire will affect your resistance. And how does it do that? Let's look at that plot many moons ago, aka Friday. Let's look at that. Okay, so this is conductivity, which is 1 over that. Oh, pardon. Okay, well, it seems to want to present the current page. Let me see, slideshow from current. Here you go. Yeah, so if you see here, conductivity decreases as a function of temperature, right? And what's the relationship between conductivity and resistance, or resistivity? That's normalized by, the area and length of a wire. It's the inverse of that. So it also changes. So temperature absolutely affects the resistance of your wire, right? So it's all of the above, which I think that gentleman already anticipated when he said, I couldn't mark all my answers. Okay, so how do you think then a semiconductor with a band gap, how do you think that would affect the conductivity of a material, of a semiconductor? Now that you don't have electrons just floating about in the conduction band.
Correct me if I'm wrong, but if you increase the band gap,
Ish, yeah. Yeah. So now you're talking about so your comment is an indirect comment to the conductivity, right? So, but how does the band gap come into play when it comes to affecting the conductivity? Is it affecting the mobility of the electrons? Is it affecting the charge carrier concentration that affects the conductivity, right? So these are the questions we have to ask when we're trying to decide how does the band gap affect the conductivity. So, just going to go through very slowly or very quickly. Okay, so let's get to that. I'll come back to that. And this, okay. All right, so bands, jumped ahead. Okay, so let's talk about that. Let's talk about the intrinsic semiconductors. So here we see, in this example, right, let's compare it to the metal. So you could see just a linear dependence of the resistivity of a metal, copper, at an elevated temperature. So here's the example for a metal at 100 C. So you can see here the linear relationship. So if you're at room temperature, let's say 20 degrees, you can look up these values, right? You can look up the coefficient of resistivity and see how that changes. If you know the coefficient of resistivity and you want to say, okay, well, what is my new resistivity at an elevated temperature? Here in this example, it's 100 degrees Celsius. You can look up the resistivity at the first temperature, 20 degrees Celsius, so that would be reported in a table. So that's basically room temperature. And then you can measure or calculate the new resistivity at an elevated temperature, right? So clearly there's a dependence for resistivity on temperature or conductivity on temperature. Okay, so that's not the case when it comes to semiconductors, because now you have a band gap. And so here in your book you see, okay, there are some known compounds here, cadmium sulfide, gallium arsenide, indium antimonide, and they're intrinsic semiconductors. What that means is the amount of electrons that you have as charge carriers is the same as the number of charge carriers for holes. Sorry, for the number of holes. Okay, but the mobilities are not the same. So let me go to that equation. Sorry, the equation was just here. Yeah. Yeah, so here we go. So the conductivity for an intrinsic semiconductor. So you have the same number of holes as you do the same number of electrons. Your conductivity is governed by this equation. Okay, and you've seen this before, right? You've seen the number of charge carriers for metals times the charge of that carrier. So when we were talking about metals, we were just talking about the charge of an electron. So we'll take the magnitude of that charge, which is 1.6 times 10 to the negative 19 joules. But here, we now have to start discussing when you excite across this band gap an electron that used to be here, if you excite it up from the valence band to the conduction band across this band gap, and the band gaps differ based on materials, as you can see here. When you excite that, you now have this electron-hole pair, and we call that an exciton, right? And so now this electron is free to move in the conduction band as it pleases, okay? Whereas your hole is less so. So you'll see that mobility from the data tables that are in your book, you'll see that the mobility is different for holes versus electrons. And this is for, of course, something temperature greater than 0 Kelvin. But the takeaway is for intrinsic semiconductors like silicon, germanium, things that you know very well and that makes up most of the semiconductor industry, the number of holes is the same number of electrons. That won't be the case when we start doping things in, and we'll call those extrinsic semiconductors. Okay, something that also came up in your textbook that very briefly is this whole notion of Fermi-Dirac distribution, or in your book it's called the Fermi function, for Fermi probability. So all that means is all these beautiful band diagrams that we have that we said, okay, here's your valence band, it stops here, and then you have some band gap, and then you have a conduction band, and if you get your electrons from your valence band to your induction band, then things move and conduct. But the reality is that at temperatures greater than 0 Kelvin, you actually have this distribution, and it's called F of E. Right? This distribution is dictated by your energy, where you are in your energy, normalized by KT. I think it's +1. Okay. So what that means is in a nice 0 Kelvin scenario, the band is very flat like that. But the reality is, as you increase temperature, the distribution of where your electron is fluctuates. And so your book has it also plotted like this, where this is energy, this is the probability. Probability is out of 1. So at some, if you rotate this by 90 degrees, it looks something like this at 0 Kelvin. And then as you increase temperature, that means there's some probability of your electrons existing at higher energy and also at lower energy than the top of the valence band. And as you increase the temperature some more, your reality becomes more like even more smeared out. This is supposed to go to 0. I just didn't draw it that well, okay? So all it means is you increase the thermal energy and your electron is somewhere in the world. It has greater likelihood of being greater than your valence band energy, but it also has a likelihood of being lower than that. Okay, so it just gets smeared out due to Fermi-Dirac statistics. Okay, and this, I'm just giving you the equation mainly because you get to derive that in your quantum mechanics class when you take it. So I don't have to rederive it here for you. But this is for particles of spin 1/2. Okay. Okay, so that's your reality. You have some band gap. You have same number of holes and electrons. You now have this smeared out probability of the electron existing somewhere. Okay. Once you excite it with temperature or light or what have you. Okay. So then let's go back to your question about, how does the band gap affect your conductivity? Your band gap affects your conductivity by way of changing the charge carrier concentration.
Quick question.
Yeah.
Is that E in the, I'm going to say absolute value sign, E like the natural number E, and then what's mu E sub E, what's mu sub A?
Okay, so it's the same mu as what we discussed for metals. It's your mobility. How easy or resistive is this electron from moving in your material? If it's just stationary, why would it move, right? So if you apply some voltage, or, you apply some electric field, then it'll start moving. But how resistant is it, right? So you excite this electron, it's going to be bound to this hole. In the conduction band, the electrons are going to be, the electrons are going to have higher mobility, right? Because they can just move in the conduction band. The hole, less so. So the mu sub E, mu sub H is your electron hole mobility, respectively. The E is not the natural log E. Typically, I try to do that more. Yeah, I can see why you would be confused by that, so I apologize. Yeah, it's 1.6 times 10 to the negative 19 coulombs. And then your carrier density. How many of these electrons do you have? If you're talking about electrons, how many electrons do you have to move within your material? So that all affects your conductivity of your intrinsic semiconductor. So you can imagine that if your band gap gets larger, right? If your band gap gets larger, what happens to your carrier density concentration? Your N sub I. That's a negative.
Oh, negative.
Yeah. literally a negative and also in response negative. That's wrong. So, right, it's e to the negative eg, right? So I say gap here, but the community also writes, that's just your band gap.
Question, what is that symbol beacon next to the E that's weirdly
This?
Yeah.
Oh, that's proportional to. Yeah. Okay. So it decreases your carrier density. But if you increase T, right, it makes this number smaller. E to the negative small number, what happens there? You're looking at the plot. I just asked you what the plot looks like. As you increase temperature, your intrinsic carrier concentration also increases like this, okay? For the same material, same band gap. So if your carrier concentration is increasing, what do you think is going to happen to your conductivity? It increases. Yeah, it's just based on the equation, it's a direct correlation, okay? So that's it. Extremely simple. Gordon Moore figured this out, founded Intel, and the rest is history, right? Oh, there's some operations in between. How do you get things on a chip, transistors on a chip? But once you figure this out, not so bad. Actually, a bunch of people at Bell Labs also figured this out. It's not just Gordon Moore, but okay. So, right. So then you can backtrack all this information out and say, okay, if I plot the log of my conductivity of my material, I can just put down a 2-point probe, right, and just measure the conductivity within my material. I can plot something that looks like an Arrhenius type relationship and backtrack out the band gap, this EG, okay? And based on this relationship, we can see that the slope is negative of the band gap divided by 2 times the Boltzmann constant, okay? So it's a thermally activated process. Again, you'll never stop seeing this, by the way, in your life. In fact, the default answer, if you had to guess, is that it's a thermally activated process. It's like guessing that your crystal structure is monoclinic. You'll be right about 72% of the time, okay, for any known material. Okay, so this relationship you've dealt with, you've manipulated. This equation is something you know and love, right? You have conductivity, you have some materials constant, and you have the 1/T relationship. Log of conductivity, reciprocal temperature. You can backtrack out the band gap pretty easily, okay? So let's do that. If you're a new processing engineer, you're part of R&D at Intel, one of the thousands of people out in Oregon, all right, and Arizona, possibly now New Mexico, and you're asked to characterize a new semiconductor. You've measured at room temperature the conductivity, which is 250 inverse ohms meter. Room temperature here is 20 degrees Celsius. And then you also measured at 100 degrees Celsius, because you just ramped up the temperature. You measured the conductivity to be 1,100, right, inverse ohm meters. So how do you backtrack out this band gap? Just analytically before we crunch some numbers. First, let's write out the equation, okay? So, okay. I'll write EXP just to not confuse you all. Okay. So we know the relationship between conductivity and band gap, and we want to know what the band gap is, right? And we've gotten very good at writing this relationship. K is Boltzmann constant. We've gotten very good at manipulating this by taking the log of both sides, right? You're comfortable with this, diffusion, all is well. Okay, well, analytically, we know that we have a log of conductivity at temperature 1. Bandgap doesn't change, temperature 1. So that's the analytical form. And we know at some temperature 2, we can write out the same relationship, right? So if we want to know what Eg is, we can do what we've done with diffusion and getting the slope of the diffusivity plot. We can get the activation energy, aka now the band gap, in the same way, right? We can say, okay, well, we take this minus this gets you 0. So we can say, okay, well, if we subtract equation 2 from equation 1, we get something that looks like that. So then we could say, okay, well, if I make this positive, this becomes negative. It doesn't really matter, because in the end, the negatives and the positives all become a wash. What?
You can use logarithmic rules to make that a little.
Correctamente. Okay, so, oops, sorry. I'm running out of space, so I'm going to be a little bit more efficient. Right, exactly what we did before. Now, if you multiply 2kT, you move it up. I'm sorry, 2k. Right, just analytically, before you punch in any of the numbers, it looks the same as when you're calculating for activation energy for diffusion. Okay? Boltzmann's constant. Okay, so that's the analytical form. In the next slide, I've actually crunched out the numbers for you. What do you think the band gap's going to be? What is your feel for what a band gap should be? If it's less than 1 electron volt, then it's a small band gap semiconductor. And so silicon's 1.1, right? We just discussed that. Less than that, you can definitely have that. What about higher than 1? You're on the order of order of magnitude. You didn't say like 100. So.
I think if you go past, I think, like 100%, you start to get a little bit too big.
3 is too big. Yeah. So 5 eV is basically starting to get 3 eV. What I said at the beginning of this module, 3 eV is basically the cutoff of what we consider like a semiconductor versus an insulator. Because if I just show you one gap is bigger than the other, how do we define that, right? We define it based on resistivity. How difficult is it to get conductivity in this material, right? For insulators, they have large band gap. It's extremely difficult to do this, right? Okay, so you can have less than 1. Obviously, 0 is just a conductor, right? 0 eV is that you don't have a band gap. But really, between something larger than 0 up to like 3 eV, that's a good feel. So if you're calculating your band gap to be like 10, 100, 1,000, that's no go. Okay. So here I wrote out the numbers. So here's the log of 20 degrees C. The conductivity at 20 degrees C. Remember to convert to Kelvin. And then once you plug in the numbers into the analytical form, it comes out to some number. Some sensical number. Okay. Okay.
So K equals 8.60 lambda.
Well, EV per Kelvin. Obviously, the units change depending on if you're using joules or whatever. Here we deal with EV. Okay. So now that was intrinsic. That was the easier case in the sense that the number of holes is equal to the number of electrons. Now, let's say you start adding in impurities, and you want to do this strategically. right? You want to add in a certain amount that will help you increase your conductivity, say, right? And this is basically the foundation of Intel. So you look at it and you say, okay, silicon has 4 electrons. Okay, so if I go 1 over, these elements, the group nitrogen, phosphorus, arsenic, antimony, those elements have 1 extra electron. So where do those electrons go? In this group 5. You have 4 electrons that will covalently bond with the silicon, but now you have 1 extra electron that's just floating, okay? And so that your electrons, it'll just be, you know, in the material. So when you apply an electric field, the electron is going to go opposite of that, right? And so if you have a lot of these atoms, if you have, let's say, Avogadro's numbers worth, then you can really think about, you know, generating some conductivity, okay, versus the intrinsic semiconductors. So it also changes where your Fermi energy is. So here for extrinsic semiconductors, for the N-type, so here we've added in some element from group 5. So you have 1 extra electron. We call this type of doping N-type, right, because you get negative charge out of it. And so the extra electrons are going to sit at this new energy level that's actually closer to the conduction band. Okay? It's not exactly in the middle. It's going to be closer to the conduction band. And we call that the donor state because you donate an electron. Already you can anticipate that if you have a p-type extrinsic semiconductor, you're going to have acceptor states, right? And that's going to be closer to the valence band. So p-type, n-type, that's where they come from. So you could see here, if this is your band gap originally, and now you are sitting at this donor state that's close to the conduction band, it's not going to take a whole lot of energy for this electron to be excited to the conduction band and conduct, and your material to conduct, right? So that's exactly what you see. For p-type, let's say you want to engineer holes. If you're silicon and you add in boron, aluminum, gallium, indium, right, you're going to have 1 fewer electron. In fact, you have 3 electrons as denoted here. So the particle that you have is actually a hole. And so where does this hole sit? Well, it could also sit anywhere, but it will go with the gradient of the electric field, right? Because it's positively 1.6 times 10 to the negative 19 coulombs. So it's going to be attracted to the electric field. So where does it sit energetically? Well, now you have this new state called the acceptor state. And this hole will actually sit somewhere here. And if you excite it, you could see that it doesn't have far to go. Okay, so now you have intrinsic semiconductors, extrinsic semiconductors, N-type, you add in 1 extra electron. P-type, you go to your left, you have 1 fewer electron. Okay, so you could think, okay, why is this going to be useful? Well, if you have the number of holes and electrons that are not the same, and you apply an electric field, you can imagine being able to engineer your material in the way it conducts. Okay, so how does your doping affect the overall conductivity? Well, depending on if it's N-type or P-type, you have different relationship. So here you see the log of the conductivity as a function of reciprocal temperature. If you just had intrinsic behavior, what we saw before, this thermally activated process, we see this slope, right? We see this regime where the slope is just your band gap divided by 2 times Boltzmann's constant. But as you decrease in temperature, so if you go this way, you're decreasing temperature. If you go this way, obviously, increasing temperature here. At lower temperature, the conductivity is dominated by the charge carriers from your dopant. So we call that extrinsic behavior. And the slope of that is defined as your band gap minus the energy of your donor state, divided by divided by K for your slope. There's this interesting region here where, so you've excited all the electrons from, let's say from your phosphorus and silicon. At some point, there's an exhaustion range, and then as you increase the temperature some more, so as you go this way, the dominating part of your conductivity lies in the excitation of your intrinsic carrier concentration. So what that means is if you dope in phosphorus into silicon, at lower temperatures, the charge carriers from phosphorus is what's being excited, and then at higher temperature, it's more intrinsic behavior. So if you plot, if you plot temperature, let me see how I can do this. If you plot temperature, where temperature is increasing this way, and let's say you're looking at the number of charge carriers for electrons or holes, it looks something like this for extrinsic, and for intrinsic, it looks like this. So all this means is that at higher temperature, the intrinsic carrier concentration dominates the behavior of the conductivity of your material. At lower temperatures, it's the dopant concentration that matters. Okay. So that's for N-type. It changes a little bit with P-type. So let's see. So you can backtrack that out. I don't have P-type on here, but the slope changes. Actually, I think I have it here. Nope. Okay. All right. Oh, sorry. For P-type, it's here. So for P-type, the slope is a little bit different. It's just the energy of your acceptor state divided by Boltzmann's constant, and that dominates the lower temperature regime. At high temperature regime, it's just your band gap divided by 2 times Boltzmann's constant. And that's it. So similar behavior governed by slightly different energetics, and that's about it. Okay, let me see if this is, okay, so we talked about Fermi distribution. Why don't we put let me see. Yeah, I don't think there's enough time for me to go into detail about semiconductor conductivity versus metal. So let's stop here because it's going to take me more than 5 minutes to go through this. So next time we'll review conductivity of semiconductors and metals, and then we'll go into semiconductor devices.